Part 3, Complex Roots of Polynomial Functions. The fundamental theorem of algebra and complex factorization. Suppose f is a polynomial function with degree n is greater than or equal to 1, then f has at least one complex zero. And actually, f has exactly n complex zeros counting multiplicities. So if we have a degree 3 polynomial, there are 3 zeros. So let's show that this applies to the following functions. We have f of x equals 2x squared plus 3x minus 2. If I factor that, I get 2x minus 1 and x plus 2. So my zeros are 1/2 and negative 2. Notice this is a degree 2 polynomial, and we have exactly 2 zeros. Let's look at g of x equals x squared plus 4x plus 4. I can factor that to x plus 2 squared. So our 0 is x equals negative 2. This is only one zero, but it does count twice because it says counting multiplicities up here in our theorem. And this one is a multiplicity too. So if we count it twice, there are 2 zeros. Determine the complex zeros of h of x equals 3x cubed minus 4x squared plus 2x. I'm going to start by factoring out an x, and I'll have 3x squared minus 4x plus 2. Now this part in parentheses doesn't factor, so I do need to use the quadratic formula. So negative 4 plus or minus the square root of negative 4 squared minus 4 times 3 times 2 all over 2 times 3. Simplifying, I get 4 plus or minus the square root of 16 minus 24 all over 6, which is 4 plus or minus the square root of negative 8 over 6. And I can simplify that to 4 plus or minus square root of 8 is 2 square root of 2. So I have 2i square root of 2 for square root of negative 8. And then everything is divisible by 2. So I have 2 plus or minus I square root of 2 over 3. And I can write this as 2 over 3 plus square root of 2 over 3i and 2 over 3 minus square root of 2 over 3i. Let's factor the polynomial f of x equals x cubed minus x squared plus 4x minus 4 to linear and irreducible quadratic factors. That means either linear factors or factors that cannot be simplified without the quadratic formula, that we can't factor any further. And then we'll factor over the complex numbers. Notice that this can be factored by grouping. Out of the first group, I can factor out an x squared, and I have an x minus 1. And out of the second group, I can factor out a 4 and be left with x minus 1. Now I can factor an x minus 1 out of both of those terms, and I have x squared plus 4. So x squared plus 4 is what we call an irreducible quadratic factor. We cannot factor that further. We could use the quadratic formula to factor it further, except for then we are going to have imaginary numbers as those zeros, because x squared plus 4, if that equals 0, then x squared is negative 4. So x is the square root of negative 4, which would be plus or minus 2i. So to factor over the complex numbers, I still have the x minus 1. Then I have an x minus 2i and an x minus a negative 2i, which is x plus 2i. So part A, I factored to linear and irreducible quadratic factors. Part B, I factored over the complex numbers.